So our topic at hand today is oxygen sensor testing and repair. There's a lot of things that the oxygen sensors are used for on a vehicle. Most often it is fuel control, right? Especially when it comes related to fuel trims. The often maybe misunderstood fuel trims. So we're going to start there. We'll start with a quick little overview of fuel trims, maybe a little review. But what fuel trim is the engine computer when it's running in closed loop, and that's what this would be an example of, a closed loop, right? It just goes around in a loop, trying to keep that air fuel ratio to 14.7 to 1, or stoichiometric. You may also heard of it called as a lambda reading, and lambda of 1 is the same thing as 14.7 to 1 air fuel ratio, right? So it's 14.7 parts of air to 1 part of fuel. So the oxygen sensor is going to read either rich or lean. So when it reads lean, it's going to call for a positive fuel trim, because when it's lean, that means it has less fuel than it needs. So we need to add fuel to the mixture. So that's why we get a positive fuel trim, and then we'll get +1, +2, what have you. Then it's going to keep going, and it's going to correct, and then eventually it's going to correct too far, and then the oxygen sensor says, whoa, 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 all right, we're rich now. So when it's rich, that means it's too much fuel, lower front number there. So O2 is rich, and then it'll say, okay, we need to pull fuel away because now we have too much fuel going into the engine. So we'll pull some fuel away. And then it continues doing that until finally it says, oh, no, now we're lean. Add fuel. And oh, now we're rich. Now lessen the fuel, right? So it just goes in a constant loop like that. And that's just how the vehicle gets run nowadays, right? So negative fuel trims means I'm pulling fuel out. Positive fuel trims means I'm adding fuel to a lean mixture. And then also these fuel trims, the oxygen sensor is leading into the short-term fuel trim first, right? So short-term fuel trim is going to react first. It's going to go either rich or lean, plus or minus. And then over time, let's say it continuously is at +4, +5, whatever percent fuel. Then eventually the long-term fuel trim is going to learn, oh, well, I guess this is normal now to be adding this much fuel. And then it in turn corrects and goes up. And then the short-term fuel trim goes down back to kind of where it was until maybe it's adding more fuel or subtracting more fuel. So this teaches into this, right? So the oxygen sensor tells the short-term fuel trim what to do. Over time, the short-term fuel trim will teach the long-term fuel trim what it needs to be doing. So you can use those as a guide, especially the long-term fuel trim. Long-term fuel trims, 10% or more on either way, then you have some sort of an issue that the vehicle is correcting for. Usually it should be only just a couple percent on either side. And then same thing with short-term fuel trim. If I have a short-term fuel trim that's double digits on either side, I probably shouldn't, but on the occasion that you do, then you definitely have a problem that's happening like right then and there, because it reacts pretty quickly what the oxygen sensors do. So let's talk about a couple different types of sensors that we have out there nowadays. And Zirconia sensors are the classic from way back in the beginning when they first started using oxygen sensors. And they use the hot gas in the exhaust in order to heat them up, because they have to be at a certain operating temperature to actually read correctly, right? So they need to be in range of about 620 to 640 degrees Fahrenheit. Now we have the very old versions, which would be the single wire ones, right? So we just got a single wire there. And then we have the newer versions, which have an integrated heater in them already. So we got power, ground, and heater power, and the signal wire. So we're going to have four wires on the newer sensors, one wire on the older sensors. Now, why did I only need one wire on the older sensors? Because an oxygen sensor, a Zirconia oxygen sensor, it's going to produce its own voltage. So I didn't need power supplied to it. I didn't need ground coming off it. It's really just a signal wire. Here's the voltage that I'm producing with this membrane in here as it reacts to oxygen in the exhaust gas. Now, another important thing that we need to note is the reference air on the back. You ever looked at the back of an oxygen sensor, like where the wires go in, and you got kind of that shield around, and there's holes in it on the back, on the top? Those holes guide down into where the membrane is, and that is your reference air from outside. So that's why if it ever gets damaged, even if it's not like broken in half or anything, if it's dented and I can't get that reference air down to the membrane where it needs to be, or enough air down to where it needs to be, it's going to cause issues with how it's operating. Because it needs that reference air. It needs to know, what am I shooting for? Because it's going to assume wherever you're driving, that should be a roughly 14.701. Because that's what it should be at sea level, give or take. 14.7 psi at sea level is what our air is too, which is kind of interesting how those two numbers work together. I don't think it's a coincidence. All right, so we have the zirconia membrane that, based on the amount of oxygen in here, goes in through these electrodes, and based on the reference air, it's going to generate a voltage, and it's going to switch back and forth, because I'm going to have more oxygen, I'm going to have less oxygen, more oxygen, less oxygen. As we talked about earlier, it's going to go rich, lean, rich, lean. And by doing that, when you're measuring it, you're going to see it switch. You're going to see it switch rich to lean, rich to lean, rich to lean. And it operates in a range less than a volt. So it's about 0 millivolts, maybe, 0.01, up to about 900 millivolts. And it's most accurate in the middle, where it's 14.701, which is roughly half of 900, which is 455 millivolts. So as we said, its ideal air-fuel ratio is 14.7 units of air to gasoline. You can kind of see the table here. So that would be lean and that would be rich. On the high end, or rich is high, lean is low. And then the accuracy is in this very narrow band between 14.5 to 1 and 15.4 to 1. So 4.5 roughly, 0.455. It's going to be 14.7 to 1. So it is in a range of a narrow band of voltage, and that's why you may have heard a zirconia oxygen sensor called a narrow band oxygen sensor. And if I were to hook up to it and look at the signal wire using a scope, it's going to cycle back and forth, right? It's going to go rich, lean, just like that, back and forth. Now, AF sensors work differently. They work on the same principle, but it's going to be different when it comes to looking at the information, and actually testing them is a lot different. It's going to look very similar on the outside anyways, right? And you can kind of see where the reference air would go in here. We can see where it's kind of crimped around, but that's where the reference air gets through there. So an AF sensor works on a wide band of voltage. Hence, you might have heard it called a wideband AF sensor. And basically, it's two zirconia sensors, like we saw before, smushed together like a sandwich. I call it a planar fashion. So it's like a thing of plywood, right? Different plies. So it's like that. And what it does, it still has the exhaust gas on the inside of one, and then as a reference air on the outside. And then we have this cell here, and this cell here, and this pump cell is going to pump molecules in between here and here to get this lambda, or air-fuel ratio, to 1. Lambda of 1, or air-fuel ratio to 14.7 to 1 stoichiometric. It tries to pump oxygen molecules in and out. So if it needs a little, this membrane is going to act like a regular zirconia sensor. So it's going to say, oh, you're too rich, you're too lean, you're too rich, you're too lean. With that, it is going to send a current, and it's going to move it in and out. So they're a little fancier, they're a little more complex, and that's why they're a little pricier compared to a standard zirconia sensor too, because it's basically two zirconia sensors together. And this is basically telling you what I just told you. So it uses an entirely different operating strategy than a conventional zirconia sensor. So this one measures the content, and then this one pumps back and forth. So it can move oxygen ions in a negative or a positive direction, depending on which way the current is flowing. Flowing in one direction, it'll get a positive. It's flowing in the other direction, it'll get a negative. And it moves it in and out. And I have a really good animation on the next slide after this. The electric current achieves a stoichiometric ratio between both cells, and that is also known as a pumping cell. And also, because of this, the air-fuel ratio sensor, or AF sensor, is going to operate at about double what a regular zirconia sensor is, about 1200 degrees Fahrenheit. And usually it's heated up in less than 10 seconds. And that's why we have heater circuits and heater elements in the vehicle. So we'll talk more about that in a little bit, why you got to maybe reset them, things like that. So here's an example, right? So it's moving the ions in and out in between the chamber, and then it is going to be reading this voltage. And by doing that, it is going to cause the current to go positive or negative, depending on what it happens to be. The more oxygen ions that move into the monitoring chamber, the less current is produced by the pump cell. So I guess it's lower goes in. So as the PCM monitors the varying current, PCM is then going to convert that current into a voltage value pit. The best way to test an air-fuel ratio sensor signal is by monitoring that air-fuel ratio voltage pit. It's really hard to test. You can't really read the voltage coming out of it because it's trying to stay at about 0.455 coming out. So the computer controls that pump circuit, and it's a very small amount of current. Low milliamp, you're not going to be able to check it with a low amp probe. You need like a milliamp probe in order to check it. And even then, it's going to be very difficult to check. So really, when we're testing air-fuel ratio sensors, we're going to be checking that voltage pit that it converts to. We want to see it roughly around like, depending on the vehicle, roughly they run in a range of about 3 to 2.4. So 2.4 would be rich, and then 4.0 would be lean. Stoichiometric is going to be around 3 to 3.3. Kind of depends on who manufactures that sensor. All right, so rich would give me a negative current flow, low current output, and then lean would be a positive current flow with a high current output. And then the computer does the math and calculates it. Now, when then air-fuel ratio sensor voltage, if you're reading that voltage, it's going to be opposite of what you would expect with a traditional Zirconia sensor. So on a Zirconia sensor, when it's rich, the Zirconia sensor is going to be high voltage, and the AF sensor will be low voltage. When it's lean, it goes the other way. So the AF sensor is high voltage, and the Zirconia sensor is going to be low voltage. So just remember that they're opposite. And we can actually show this on the next screen. I got a data pit capture here. Remember how I said we had to watch the voltages. Now it generates, it has a bias voltage around 3.3 volts. That's what I kind of misspoke on a couple slides ago. So there's a bias voltage around 3.3 volts. But what we want to see when everything's operating the way it should, we want to see about a volt. So roughly 1 volt. So we see this is 0.99. Go to the next frame, it's going to be 1 volt. So 1 volt is normal. That's what it should look like. And you'll notice this is where we introduced a lean condition on this vehicle. So when the rear oxygen sensor was running like 0.8, which is normal, that's where it should be. And then when it went lean, it went all the way down to 0. And then the AF sensor went all the way up to 1.12. So it's very narrow range. You're looking going down by like 0.16 to up by 0.12. So it's not a huge difference in voltage, right? We're talking milliamp or millivolts. And also, this is on a Subaru, right? So they call their short-term and long-term fuel trims a little bit different. So it makes sense if you think about it, though, why they call them what they do. So the short-term fuel trim is called air fuel correction. So that's what's correcting right now. Here's how I'm doing it while the vehicle is running. I'm correcting that air fuel ratio to keep it stoichiometric. Versus the long-term fuel trim, they call air fuel learning. So it is learning what the short-term fuel trim is doing or what the correction is doing, and then adding blocks and going up and going down. So rear oxygen sensor goes lean, and then all of a sudden it goes a little rich. And then so what we did is we introduced a vacuum leak using the brake line hose on a vehicle. So it was going up to 35% correction when we leaned it out. Then as soon as we closed it back in and reinstalled it, it went negative fuel trim because at that point it was already pumping way too much fuel into the cylinder. So then it went full rich. So then it sent the lean command. So that's why we get a negative lean command. And then the AF sensor went rich. Rear O2 sensor on this one, which is Zirconia, went rich as well. So you can see how they go opposite. And then how the long-term fuel trim learns off the short-term. Notice how it lags behind, right? That's by design. That's just the way it works. So that's kind of a good visual as to how you can see how they operate. And if you were to watch all this information on a scanner, that's roughly what you would see. So about 0.8 volts normally just idling. Should have about 1 volt in the air fuel sensor. And then short-term fuel trim should only be a couple % either side. Long-term fuel trim, same. Operating temperature is also critical. So that, like I said, the difference between the air fuel ratio sensor and the Zirconia sensors operates about double, about 1200 degrees Fahrenheit. Very critical. So a pulse width controlled heater circuit is usually used for a precise heater control. Sometimes you need to reset them, sometimes you don't. So for example, on a Chevy, I know I've told this story probably 1,000 times in my career, but still a lot of people out there that don't realize it needs to be done. So on this is after relearn on a 2013 Silverado. This goes all the way back to 2006 through current day. You replace oxygen sensors on here. You need to go do a code clear with a scan tool, regardless of whether or not a DTC is set. So they want you to wipe out the monitors. And then the oxygen sensor heater resistance learn reset needs to be done with a scan tool where available. Perform the above in order to reset the oxygen sensor resistance learn value to avoid possible heated oxygen sensor failure. Right? So over time, it's going to learn that the resistance in the heater circuit has increased, so it needs to increase the amount of current flow or the pulse width on the heater control circuit in order to keep it heated up the same. If you put a brand new sensor in there expecting to see like a much lower current than it's getting, and it's getting fed that high current because you haven't reset it, you will burn out that element pretty quick because it's not prepared for it. So you definitely, it could be oxygen sensor failure. It would fail in the years. Very simple though. It's just a simple reset box on the tool. So you just click on reset and then it will reset. Also, other vehicles have the same thing, but you might have to do a slightly different procedure. So for example, on Nissan, who I talked about last week, they have a learning heater circuit as well. But in order to reset it on that, it's a mixture learn self-learning control. So we need, basically what that does is takes the air fuel mixture, takes it back to normal or factory level, and then so it's going to tell you what your air fuel ratio is, and then it'll just continue, and then it'll reset it back to it. Another thing that oxygen sensors are used for is calculating catalyst efficiency. So since it's reading the amount of oxygen that's in the exhaust stream, we can see whether or not that catalyst is catalyzing and putting the proper amount of oxygen. So I'm not going to go through a whole big spiel on how catalytic converters work, but the bad stuff goes in, the less bad stuff goes out. Water's not too bad, carbon dioxide, oxygen, nitrogen, right? So those go out after being oxidized. So we can see this by using the oxygen sensor. So if I wanted to diagnose a cat and see if the cat was working, I can use my oxygen sensors by looking at both the front and the rear. More on the rear than anything. And I would say still the majority of vehicles out there most likely still use a Zirconia sensor in the rear. Most vehicles have gone to an air fuel ratio sensor in the front, bank one sensor one. But same example, Subaru Forester, it's got an air fuel ratio sensor in the front, it's got a Zirconia sensor in the back. And how you're going to do this, how you're going to test it, is you're going to want to see your rear oxygen sensor voltage, your air fuel ratio sensor voltage, and then in this case I had throttle angle there because I just wanted to make sure I was keeping a steady throttle, and what your vehicle speed is. So what you would do is you would get these graphs up, and then you want to drive the vehicle on an open road for like maybe 2 minutes, and you want to be able to maintain a steady 45 to 50 mile an hour speed. So in this case, I had a pretty straight road, not really any obstructions in my way. I was able to go 50 miles an hour for, a little over probably a minute and a half, 2 minutes. And what we should see is something like this. Should see the air fuel ratio sensor in the front barely moving up and down. This is like 0.99. It goes to like 1.99, 0.98. It's keeping fairly steady. Keep a steady throttle so we're not introducing any air fuel ratio changes. And then a steady speed, so also we're not introducing any changes. The load should stay pretty much the same. Should be fairly flat. If I'm trying to go up a hill, it'll probably make it a little off. What we really want to watch is this rear oxygen sensor. If my catalyst is working properly, I should just see a flat line, and it should be on the higher side, which indicates lean, which indicates Oxygen, lots of oxygen. So that means my catalyst is working. However, if I were to look at this rear oxygen sensor in the same situation where I'm traveling at a flat, steady state of speed, steady throttle angle, steady air fuel ratio sensor, and this thing's going up and down like nuts, just going switching back and forth, rich lean, rich lean, rich lean, rich lean, that just means the straight exhaust is just getting right through, and it's not working. The catalyst is not working at all. It's just basically just not doing anything. That might as well not even be there at that point. So you could easily see that if it's switching voltages back and forth. So I thought that was a really cool trick that we learned back at the dealership, and it still applies to pretty much any car that has an AF sensor in the front and a Zirconia sensor in the rear. You could even do two banks. You had AF sensors in the front and Zirconias in the rear, even if you had Zirconias in the front. The main deal is we need to have the Zirconias in the rear. All right, so very simple. Like I said, steady throttle, steady speed, 45 to 50 miles an hour for over a minute, and then just monitor that rear O2 and make sure it's not going crazy. If it's going crazy, probably got a bad cat. We diagnosed a ton of bad cats now. And another thing we can do on this too is measure reaction time on the sensors. So what you do after you do your cruise, well, I'm probably going to need to slow down anyway, so I'm going to lift my throttle. So in this case, we lifted the throttle, went to 4%, because that's about as close as it can get when we're idling. But as soon as we went to that basically closed throttle, full release, what's going to happen? Well, my injectors are going to shut off, right? So it's going to go into coast mode. So it goes, so I should see full. Oh, wait, no, I should see rich. Never mind. So foot off the gas, and then it went up, and then that went down. That's lean. Rich. I misspoke. It should be on the high side, and that's low side lean. But I should see my AF sensor react first, and then my oxygen or my front sensor react first, rear sensor react second. Does that make sense? Because it took that long for the exhaust to get from there to there, right? So I should see this sensor react first, that sensor react second. If this sensor lags and reacts second, then I know I got a lazy sensor in there. And there is a spec for it too as to how long it should take, but I don't know that one off the top of my head. And it's going to vary by vehicle anyways, just because of the distance, right? So I should see normal operating there, and then when I lift the throttle, it goes lean, so that's up and that's down. I misspoke. Okay, let's go live on the tool. Show you how to get a little bit more information. All right, so first off, if I want to test my oxygen sensors, I can test Zirconia sensors, no problem, right? So if I want more information on oxygen sensors, and I have a tool with the guided component test function, so like a Modus, a Triton, a Zeus, a Varus, one of those. Guided component test is your friend, because you can go in here, and if you go into classes, the very first thing, and you go to how to, you will see all these different classes that are in here. And if I go way down to the bottom, oxygen sensor and feedback system analysis. Tells you about air fuel ratios, how they work, what you should be seeing on the scope. Or on my data stream. PCM response, heated oxygen sensor, what I should see. It's going to tell you resistance ranges and temperature ranges and stuff you should probably see. Non-heated oxygen sensor is going to be a little bit different. Open versus closed loop. We'll talk about that. Oxygen sensor types. And then understanding oxygen sensors, post-catalyst and pre-catalyst. So pre-catalyst to be your front one, obviously. And then post-catalyst oxygen sensors in there too. You should have a relatively flat output. A normally operating post-cat O2 should have a relatively flat output. An inefficient converter will cause peaks and valleys in rear O2 sensor signals similar to the front O2 sensor voltage. It's going to go up and down just like that. Post-cat O2 is slow to react or inefficient. If the cat converter is effective, the PCM will set a code. All right, so that is where you could find that information. That's just right in, like I said, under classes. Don't ID a vehicle. Go in there. Another thing, we'll go in on our GMC Acadia here. And if I go into, say, service resets and relearns, And I go down to replace or relearn oxygen sensor. And I go to functional resets. It's going to be right there, oxygen sensor heater learn. You go in there, it's going to tell you what the current is. And then you would just hit reset. It resets all 4 of them back to factory. And even if I didn't replace all 4, it will relearn where everybody needs to be. That's the key. It's going to relearn it back to where it needs to go. Get it better. Let's go on the Nissan. Rogue Sport. I'll get back to that in a sec. I think it's got a better list on Nissan. So on the Nissan, it is engine adapters, right? Oops, wrong way. So they call that resetting engine adapters, right? For the reset the oxygen sensor. Just go and pick one. There we go. So it's called self-learning control on there. And what it'll do is it allows the mixture ratio self-learning control value to be cleared. Improper uses may cause poor drivability when the ECM self-learning is completed. So it's basically if you didn't replace anything and you just clear it, it might run odd until it self-learns again. So it's going to tell you your percentages, hit continue. And then it's just going to wipe them out and it brings you back to the main menu. That's all it does. Let's go back in here again. This time we'll go on our road. Let's see if there's any. Oh, oxygen sensor delayed response. That's a good one. See some information in there. So to judge malfunctions, this diagnosis measures response time of the AF signal computed by the ECM from the AF signal 1, sensor 1 signal. Time is compensated by engine operating speed and load, fuel feedback control cost, and AF sensor 1 temperature index, based on whether compensated time is inordinately long or not. And then it just gives you the criteria, what you need to see. And it says to use a scan tool to test it as well. So that's just one example. There's other ones I was trying to think of, like heater control circuits. So there's signal circuits or signal codes, low voltage, high voltage, slow response, that sort of thing. That's more of a voltage. Or it could be a heater. So if you get an oxygen sensor heater circuit code, it's not necessarily the actual sensor itself. I mean, yeah, you may end up having to replace it, but in that case, you would want to be testing the heater circuit, not the actual output from the oxygen sensor, if that makes sense, right? So you need to be cognizant of what the code is telling you, what kind of code it is. Is it a signal code or is it a heater code, right? Because those could be 2 totally different things. And then this one with the slow response might be a little bit different testing procedure as well versus a voltage type of test. Probably 9 times out of 10, you're going to end up replacing the sensor for any of these things anyways, but especially for a heater problem, it could just be a bad relay. It could be bad wiring. So you always want to make sure that you're testing the right thing. Yes, you're still testing the oxygen sensor, but am I testing the signal or am I testing the heater? Or am I testing the ground? What am I testing, right? You just got to be cognizant of that as well. All right, with that, that is oxygen sensors. Let's talk about what we're going to talk about next week. Next week, we are continuing on our ever-present OEM-specific training, and next week it is on the ever-present Mercedes-Benz. There is an interesting trend that I will mention on the Mercedes-Benz when we get to it next week that I noticed in the sales numbers for sure. But we'll talk about what makes them tick, what makes them unique. There are certainly some unique things in there. I'm already collecting stories from other techs on their tips from the tech section, so that should be some. I got a couple of pretty good ones that I need to put in there. So same time and same place as always, every Tuesday, 6 to 9 Eastern. Go to snapon.com/OT if you want to watch on Zoom. Otherwise, 6 p.m. goes to our YouTube channel, youtube.com/snapon-diagnostics. Make sure you like and subscribe. 9 p.m. Eastern class goes live to my Facebook page. So it's facebook.com/snaponjason, all one word, no dash in the Snap-on. You can go check them out there. Otherwise, we also have all of these episodes readily available for free, all on our YouTube channel. Everything from Intro to ADOS to our OEM-specific training on Nissan that we did last week, and everything in between. This is actually episode 93 right now. If you scan that QR code, you will automatically go to the page and subscribe. So that's helpful. Otherwise, you can go to youtube.com/Snap-on Diagnostics. Like I said, all readily available for free whenever you need it. And, check it out. It's free diagnostics training, right? Who offers this month? Also, do we have your email address? More than likely we don't, because unless you gave it to us at the time where we activated your scan tool, we probably don't have it. But if you don't have it, you're missing out on some good information. So things like technical focus articles, SureTrack blog, quick tips. Here's a technical focus article on diagnosing a stretched timing chain, right? Here's what it would look like with a worn out timing chain. And, just a bunch of stuff like that. New product releases, they'll announce like my schedule a couple months in advance as well. Just so you're aware what's coming up, right? We don't spam you with a bunch of stuff. It's not going to be a bunch of marketing, stuff, here, buy this thing. It's not like that. It's going to be more of the technical focus type content. And then if there is a new product release, we'll at least let you know, right? So, that is worth it, your time and effort to sign up. Keep in the loop. All right, time for questions. Before I do, real quick, let me make sure that I talk about my buddy Keith and his new product training that he does. So he also does free diagnostics training every Wednesday and Thursday. Wednesday's on Zeus Plus. Thursday is on Apollo and Triton tools. So 7:30 Eastern, 6:30 Central, one class a night. Go to snapon.com/OT to sign up. It is Zoom only. It is kind of designed to have you sitting down there in front of it, watching what he's doing on the screen while you function through the demo vehicle on your screen. That way you can get the most out of your vehicle or most out of your scan tool, sorry. He does it every single Wednesday and Thursday. Like I said, different tools. The first hour is going to be setup functions. Let's make sure your Wi-Fi set up. We'll talk about security link. We'll talk about cloud and a few other things. And then he gets into fast track intelligent diagnostics, code to completion, guides you through it, kind of discusses how that's going to help save you time no matter what on a code. And then that's about an hour. Then he takes about a 5-minute break. And then after that, it's about 45 minutes or so on the scope functions. So got a component test, lab scope, graphing meter, digital voltometer, all those different things on the tool. So definitely worth your time. If you want to get a little bit more knowledge on how to operate your scan tool, that's where you want to go. All right, let's get to questions. Got a few on Zoom right now. Let's see. Martin says, what about a plugged converter? So a plugged converter, I'm going to say, I don't know what the rear sensor would look like, but I know it's probably going to be lacking serious power for sure, especially if it's plugged. Every plugged cat I've ever run across had like ridiculous lack of power. Not sure what the rear O2 sensor would be. It could be going up and down because technically it's not working at that point. But you're also not going to be getting a lot of exhaust flow going through. So I'm not really sure how severe the peaks and valleys would be thinking it through. So best I can help you. Let's see. John says, should you do an oxygen sensor relearn after disconnecting the battery? I would say no, because that is going to reset all the self-learning on the vehicle anyways, unless you're using a battery maintainer. And even if you're using a battery maintainer, that wouldn't wipe out the memory on the computers and you didn't change anything. So yeah, if you disconnect the battery and you don't use a battery maintainer, it's going to wipe it out anyway. So I would say no, you don't need it. Jay said, hello, once again, helpful class. Thank you. You're very welcome, Jay. Thanks for chiming in. Appreciate that. All right, let's go to YouTube. On YouTube, Nick checking in from London as always. Thank you very much. JLE Lobo is also checking in, saying hi as always. Nick is a ride or die, man. He's always here, and I definitely appreciate it. He even watches my UK videos too, which is the same video, but hey, you can never stop learning, right? And Donald also says, thanks for taking the time to provide training. You're very welcome. David Gutierrez says, thank you. Mike Lewis says, thank you. Donald Hopkins says he's excited for Mercedes next week. Good stuff. Excellent. Colonel Buckshot says, are Chevy and Nissan the only ones requiring oxygen sensor relearns? There's the only two I've really heard of. There could be more. What I would suggest is if I do oxygen sensor replacement on a vehicle, I would at a minimum reset the fuel trims or any other sort of self-learning that the computer might do, just so it can learn back to where it needs to go. Just because, you know, it's not really going to affect the heater as much as it affects the mixture at that point. Because the fuel trims will be in a certain spot because the oxygen sensor maybe wasn't reading right, and then it'll throw it off and it'll be running way too rich for a long time or way too lean for a long time. So it's good practice just at least wipe out the fuel trims if you have that availability on the vehicle. I would do that. Colonel Buckshot also says, what year did Nissan start requiring oxygen sensor relearns? I know I've seen it as far back as the mid-teens, 20 teens. Could be earlier than that. I'm not sure. And their service information isn't very good, so it's not really like it says in the information it's required to do it. So I would go more with if I replaced it, I probably want to redo the fuel trims and self-learning and stuff. All right. Excellent. So with that, come on, there we go. Thank you very much for spending a little bit of time with me. Hopefully we got a little bit more grounded on oxygen sensors. Hopefully you'll join me next week for our OEM training on Mercedes. With that, enjoy the rest of your week. Enjoy your weekend. Have a good night and take care.